Hello, welcome to Lecture 10. In this lecture, we're going to get started on a part of the course that students have traditionally found a little bit challenging, and that's using integrals to calculate electric fields. I've made some changes to the course compared to years past to hopefully make this part of the course a little bit easier to understand, to make it more in line with what you've learned in math class. So there's been some trimming and revamping. If you've done the class before, you may notice some changes. I'll take my time going through it, and hopefully we'll get through this pretty well together. So let's start with the definition of what is a continuous charge distribution. We know what a point charge is. That's what we've been working with all along. It's a little dot, and technically it has no size. You might think of it as a sphere with radius r equals 0, but it does have a charge. So that's what we mean by a point charge. Of course, that's not actually very realistic. Real objects have sizes and shapes. So let's think about what happens if we take our little object and we put a bunch of them together. So I put two little objects together, it gets bigger. Put three little objects, it gets bigger still. Put in a fourth little object, all of a sudden it's looking like a line. So we can think of any solid object as being comprised of a whole bunch of these little point charges. That's what a continuous charge distribution is. It's a whole bunch of little point charges together, and together they form one solid object. So if you can think of any kind of solid object, you might imagine a ring or a pencil or a marble or a book. Those are the kinds of shapes of objects we'll be talking about. Your books will cover and most first year physics textbooks will cover the electric fields due to solid lines of charge, rings of charge, disks of charge, planes of charge, and spheres of charge. So most textbooks will go through the math of using integrals to find those electric fields. I'm going to discuss it conceptually with the line of charge. So this would be the line of charge. So we'll develop the concept of using an integral to find a field, just talking about the line. Then we're going to go ahead and apply the math to a ring of charge. If you're interested, by all means, have a read through your book to see a discussion about a sphere or a disk or a plane, but you won't be responsible for knowing that in this course. Let's start our process now by asking, what if we had 7 point charges, each with the same sign and same magnitude? How would we find the electric field at point P? Well, we would go through the steps we've outlined previously. We would draw the electric field vectors. Okay, so charge Q1 will have an electric field that points away from charge Q1, and we'll label that E1. Okay, I'm not going to do Q2 next. I'm going to do Q7 next. Q7 is positive. It will have an electric field that points away from Q7, E7. Maybe by me drawing that, you can see why I did 1 and 7 as a pair. Okay, if you look at those two, you might notice that the y components cancel and the x components add up. Okay, let's keep drawing the vectors. Let's do number 2 next. So there's E2. And this sort of symmetry becomes very important. And we'll do Q6 after we do Q2. There's E6. All right, next let's do Q3 and 5. There's E3. Here's E5. Again, the y components are canceling and the x components are adding up. Last, we'll do Q4. That one doesn't even have a y component. That one's only got an x. There's E4. Okay, so we would start by drawing the vectors. Next, we would find the magnitudes. And to find the magnitudes, we would know that the magnitude of each individual electric field, so I say EI, it might be E1, E2, E3, E4, so I is just a number, is K times Q. every charge is the same, but you could label it qi if you wanted to, divided by ri squared. And r is the distance between your charge and your point. So for q1, this is r1. R1 and R7 are the same. And then for Q2, this is R2. R2 and R6 are the same. This is R3. R3 and R5 are the same. And this is R4. Okay, so your R's are different, but your Q's are the same. So you would find the magnitudes. After you found the magnitudes, you would find the components. As you found the components, you might notice the symmetry and cancellation. And then you would find your answer as a vector by doing a vector sum. So you would say that the net x component would be the sum of all the individual x components. And you would say that the y components would be the sum of the individual y components. And your net electric field vector E would be the x components in the x direction plus the y component in the y direction. Okay, this is a problem we've already worked through. Let's use this concept of the fact that we would have to add up all the electric field vectors to get the total electric field. But let's start to change from point charges to those finite objects, the continuous charge distributions. To get to the idea of a continuous charge distribution, let's exaggerate what we have here. So let's say we have 7 charges and we push them close together, starting to look like something. So we push the charges qi together. Okay, next step, we really exaggerate it. We don't have 7 charges, we have a gabillion charges, and we push all those really close together. Now we have what's called a line of charge. This might be like a piece of copper wire. So we push many, I said a gabillion, technically it's infinite, and each of those charges are very small, so many small charges very close. This makes what's called a line of charge. So this is something like a wire. Technically, a line of charge is one-dimensional. It has length, but it doesn't technically have any thickness. Okay, let's get some of our notation down. In our 7 charges, we called each charge qi. In our line of charge, we call each small charge dq. Okay, this is really important. D and Q, in math class, you're probably familiar with seeing dx. D and Q are not two separate symbols. Together they make one symbol, and a dq is what's called an element of charge. And an element of charge means a tiny bit of charge. So our many small charges here are dq, and the name is the element of charge. So each little individual charge on our picture here made an individual electric field. So the magnitude of each individual electric field made by qi was ei. That was k times dq, or sorry, got ahead of myself, k times qi over ri squared. When we have our line of charges, if we have a little charge, it only makes a little electric field. So we have dE. And dE is k times dq over r squared. We still have to deal with our components. So the x components is the sum of all the individual x components, and the y component is the sum of the individual y components. Same thing happens over here, but when we have a case of many small things close together, our sum becomes a little different. And that sum sign, my first year math teacher told me this, and it kind of made sense. I'm not sure if it's really true. A stretched out sum sign is actually an integral sign. So according to my first year math prof, Dr. Gunther, he said that now our EX is the sum of all the individual little x components, but the sum of a whole bunch of little ones is an integral. And then our y components is the sum of the y components. And overall, as a vector, our net electric field vector is the sum of the individual electric field vectors. Same thing is true over here. Our net electric field vector is the sum of the individual electric field elements. Okay, so when we have individual charges, we calculate individual fields and add the vectors. When we have a line of charge, we have to think about what does one element do, and then we still have to add together all of those little electric fields, but this time when we have a gabillion small things, an addition is really just an integral. Okay, hopefully that was clear. Please get in touch with me if you have questions.